Yeah. Hello everyone. So I welcome you to this live interaction session for the course Introduction to Abstract Group Theory. Let me share my screen. I hope it's visible now. Okay. So uh, am I audible?
Yes, sir.
Okay. So we were supposed to discuss assignment 5. So let me just share the first question. Here it is. Is my screen visible to you or it is being stopped?
Not yet, sir.
It's showing stopped. So let me just reshare. Is it visible now?
Still no, sir.
Some technical. So let me just share my entire screen. I think that would be better.
Now it's visible.
Okay. So thank you. The first questions ask which of the statements are correct. So all groups here are abelian and of order 924. We need to see whether an element of a particular order is there inside the group or not. So in the first uh, case, it is asking about an element of order 2. So is it inside the group?
Yes, sir.
Reason
Due to the Cauchy's theorem.
due to Cauchy's theorem. And so the first one is correct. So the reason, as you pointed out, due to Cauchy's theorem. I should write Cauchy starting with capital C. Yeah. So what about the next option? Uh, does there uh, will there always be an element of order 4?
No, sir.
Reason 4 is dividing the order, so it may be. Or if not, then you need to tell me at least one such example. Can you construct some example where G is an abelian group of order 924 and it doesn't contain an element of order 4?
I'm trying. I haven't yet come up with an example, but I'm thinking.
Okay. Del, do you want to say something? You have something in uh, what kind of abelian groups you can construct which has order 924.
So the uh, cyclic group and the dihedral group.
Good. A
Mm.
dihedral group is not abelian. If you remove the word abelian, then the dihedral group will work because uh, it will have order 924 and there will be a cyclic group of order uh, 462 and then so let me first tell you for non-abelian case, but I should not write it because this is not a solution. So let me just speak it out. So if the option doesn't contain the word abelian, then dihedral group would have worked because in dihedral group you have a cyclic group of rotations which is of n by 2 order, and so there will be a cyclic subgroup of order 462, and then there will be reflections only apart from the elements inside this cyclic subgroup. Now, if you have a cyclic group of order 462, so something is an inside this any element which is inside this subgroup will have the order that divides the order of the subgroup and vice versa. Whatever is dividing the order, there will be a element of that order. But 462 is not divisible by 4, right? To divide it by 2, you will get 261, which is not, sorry, 231, which is not again divisible by 2. So it's not divisible by 4. Thus, dihedral group of order 924 doesn't contain an element of order 4. Clear?
Yes, sir.
But here we are supposed to get abelian groups, right? So you might not be aware of the fundamental theorem of abelian groups that might come a bit later, or you can search it for your own interest. But what does it say? It says that any abelian group is just a, direct product of cyclic groups. It may be a cyclic group or it's a direct product of cyclic groups. And you can take various kind of direct products, and that actually gives you all possible non-isomorphic groups. For example, a group of order 4. How many abelian groups of order 4 you know?
Mm. All uh, all groups of order 4 are abelian, right? So,
But how
oh, okay,
many
so
are
the cyclic group and the clean group.
the Klein group? So cyclic group is just Z4, right? And Klein group is isomorphic to Z2 cross Z2. Okay. So there are just these two groups because there are just these two kind of direct product of cyclic groups are there. Now, if I ask you, uh, what is the possibility of having what kind of order 8 abelian groups you know? Then there will be a cyclic group of order Z8, right? You can write 8 as 2 into 2 into 2. So there will be an abelian group corresponding to this Z2 cross Z2 cross Z2. And you can also write 8 as 2 into 4. So there will be one more, which is of type Z2 cross Z4. These are the only possibilities for abelian groups of order 8. Z2 cross Z4 is same as Z4 cross Z2. But if you have co-prime orders, like if I ask you how many cyclic abelian group of order Z6 are there, then there will be a unique one. Why? Because Z6 there. Now, how you can do the prime factorization? You can just write 6 as 2 into 3, right? So the corresponding abelian group will be Z2 cross Z3. But there is again a statement which says Zm cross Zn is isomorphic to Z m times n if m and n are co-prime. So Z2 cross Z3 will again be isomorphic to Z6. So there will be just one. Now in this case, what you can do, you can write 9 to 4 as you its prime factorization. So there will be two powers of 2, right? And then you will get, I think, uh, 2, 3, 1, right?
Yes, sir.
Which is divisible by 11, right? You know the divisibility rule of 11, right?
Yes,
You
sir.
take alternate sum of alternate digits and then divide it, subtract it. So here the sum is 3 and 3 is there. 3 minus 3 is 0. This is divisible by 11. So the number is divisible by 11. So there will be 11. And uh, if you divide it by 11, you will get 21. So this will be the prime factorization for this. Uh, now, and this we can keep for all the cases. Now see, this part will always give you an a unique group because this is not going to change. So Z11 cross Z21 is isomorphic to Z26 231. So you cannot get more examples through that. But this part has some power. So you can take either a cyclic group here or a Klein group. If you take a cyclic group, the corresponding group will have an element of order 4. And if you take a Klein group, then there won't be an element of order 4. So take G to be uh, Z2 cross Z2 cross Z11 cross Z21, right? Now these three are co-prime with each other. So you can simply write it like Z2 cross whatever is pending Z462. Now this part does not have a element of order 4, right? This does not have an element of order 4, and the order of an element in the direct product is the LCM of the order of its components. For example, the order of some element A comma B is just the LCM of order of A and order of B, right? So here there is no element of order 4. Here there is no element of order 4. So the LCM cannot be 4. So this group has no element of order 4. Okay. So then order of G is clearly 924, but G has no element of order 4. Okay. So is it clear?
Yes, sir.
Now, if I ask you how many non-isomorphic abelian group of order 924 are there, can you tell me?
There are two of them.
There are two of them. One is Z2 cross Z462 and the other will be Z924. Okay. Because only change is coming through this power. Clear?
Yes, sir.
Okay. Now the third case that G is an abelian group of order 924. Does it have a element of order 9?
No, sir. Um,
Reason?
Due to Lagrange's theorem.
Due to Lagrange theorem. Lagrange, an application of Lagrange theorem, you can tell. Because Lagrange theorem precisely says the order of the subgroup divides the order of the group. It comes as a corollary of that. Mm. So 9 does not divide 924. Therefore, there exists an element of order 9 in G. Okay. Okay. Now what about the last one? Again due to Cauchy's theorem. Because 11 is a prime. uh, First and fourth are correct due to Cauchy's theorem. Okay. I hope it's clear.
Yes, sir.
Okay. Then. So let me just take second question. Again, we need to choose the statements which are true. First one says every group of order 12 is abelian.
No, sir.
Is it?
No.
Can you
So
give me some counter example?
it's 3 cross Z4.
S3 cross Z4. What will be its order?
Well, oh, sorry, this is 12, right? Sorry, I got confused.
But you are almost there. Instead of Z4, can we
It's
take
3 cross Z2.
Z2,
Yes,
right?
sir.
Hmm. Uh, so take G is equal to S3 cross Z2. Then order of G is 12, but G is non-abelian. Can you give me one more example?
The dihedral group instead of S3.
No, dihedral group of order 12.
Of order 3. Sorry,
Order
order 6.
D6 you mean to say, right? Order is 12. So, not just second. The same A part and B also. Take G to be just D2 into 6, dihedral group of order 12. Then also G has 12 order, but G is non-abelian. Correct?
Sir, I have a
Yeah.
notation confusion. So for the dihedral group,
Hmm.
so the order is decided by the um, so if I'm given D2n, then the
Uh-huh.
order of the group will be 2n, right?
So, in some books, uh, uh, dihedral group of order n is written as dn. In some group books, it is directly d times. Uh, so it is written like d2n. I prefer this notation because so for example, in this case, you can write d12 or d6 or d2 into 6. 6. 6 is 2 into 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 6. 6 is 2 depending on which book you are following. Mostly people don't use this one. They either use this or this. So in this case, they say the order is D, uh, 2 times n, that is 12. But this is already indicating that you are writing like 2 into n. So this will clearly say uh, the order is 12 only. So I usually prefer uh, this notation, but people also go with this notation. But this is very bad. This is really confusing, the third one. So you can write it as D6 or D2 into 6, whatever you want. Okay.
Okay, sir.
It's just a matter of uh, uh, which book or which notes you are following. For example, D3, to say D3 is very common, but people do say it like D2 into 3 to say that it's a group of orders 12, sorry, 6. It's just a matter of convention. Okay. That's why in most of the places, whenever people do write some DN or D2N, they specify that what does it mean. Okay. So this is also non-abelian, right? And why this is not as same as our previous example, S3 cross Z2, why these two are different? Both are non-abelian, both are of order 12, so they can be same and also, right? But I have written them as different examples. Uh,
Mm. So there can't exist any isomorphism between
that is
D2 and D6. Or
obviously
I'm
people.
trying to say, I'm trying to see
Why?
what.
They are different means that there is no isomorphism. So how you figure out like two groups are not isomorphic?
I assume that they're isomorphic and then I come up with some contradiction.
Uh, that is the last step, I will say.
Okay.
First, you try to see whether they are satisfying all properties, uh, uh, simultaneous properties, like uh, both are abelian or both are cyclic, both are non-abelian, both have same order. What are the possible orders in those groups? If that is also same, then for each given order, uh, how many elements of that order are there in both the groups? That this last steps mostly work out for most of the cases. That two groups having the same uh, type of orders and corresponding to each order of element, the number of elements are same in both the groups. Then it mostly turns out that the group is isomorphic. So in this case, abelian cyclic part is done. Both are non-cyclic, both are non-abelian, both have the same order. What are the possible orders for S3 cross Z2 and D26?
So can you repeat the question?
So what are the possible orders for S3 cross, uh, I can write as G1, G2, that would be better. What are the possible orders for G1 and what are the possible orders for G2?
The
Group,
order is just
order of
one.
elements, order of elements.
Oh,
Hmm. Group
so for
order is,
given it's for I think for G1 it's um 1, 2, 3 and um 12, but I need to check.
12. If there is an element of order 12, it will be cyclic. One,
So
two,
since
three,
there's
and
like two, only two is possible.
one or two is possible, right? And
Yes.
here, one, two, and three, right? And the order can be LCM of these. So this will be just one, two, three, and six. If there is an element of three here and element of order two here, then that pair will have order six, right?
Yes.
Okay. And for D26, the same thing is there because there are reflections. There is a cyclic group of order six here, and uh, there will be uh, an element of order 3 because the group there is a cyclic subgroup, so all possible orders will be there. But still, uh, they are not isomorphic.
Does G2 have an element of order 4?
G2 has an element of order 4. What will be that element? No, there are reflections. So for dihedral group, there are six reflections. There are n reflections for uh, group of order G2n, and all possible elements coming out of the cyclic group. So one more element of one rotation of order, there will be just identity element, right? And uh, then uh, one rot one rotation of order 2, one rotation of order 3, because all these are coming by the rotation are 360 divided by 6, right? So R60. So our rotation of order 180 will have order 2, rotation of uh, order 120 will have order 3, and the remaining will be rotations of uh, order 6. Just look at as that 6. How many elements of order 1, 2, 3, and 6 are there? So three rotations of order 6, right? So this is same as your 1 bar in that 6. So 1 bar will have order uh, 6. 2 bar will have order 3. What is 2 bar? R120. 3 bar will have order 2. That is uh, just a minute. 3 bar will have order 2. It's a rotation of 120. What will be 4 bar? 4 bar will also have order 3, right? So there will be two rotations of order 3. Sorry. And then uh, 5 bar and 1 bar both have order 6. So there will be two here, and one is identity. So now, if that is the same case with Z6 cross S3 cross Z2, then I will tell you to prove that these are isomorphic. I may be wrong. I just thought the example here. So uh, what is this order data for ST cross check 2? How many? There will be unique element of order 1. That is okay. Uh, what is the possibility for order 3 elements? Sorry, order 3 elements. Here you have 2 cycle, sorry, 3 cycle, and here you have uh, 0 element, and again here is 3 cycle and 0 element. These are two elements of order 3. If you want order 2 element, then how many will be there? Any element of the form AB, where order of one of them is either identity or 2, right? So how many possibilities of order 1 or identity here? 4, right?
Yes.
You can take any 2 cycle or identity. And how many possibilities of order 2 are here? 2, right? 8.
Yes.
But if both are identity, then they will have order 1. So you need to minus that possibility. There will be 7 elements of order 2. How many? So here there are also 7 elements of order 2. Order 3 elements are also matching. Identity is also there. So now 2 rotations of order 6. So order 6 element are also there in the same number. 1, 2, 3, 1 and 1 bar, and here you have 1, 3, 2, 1 bar. Both these will have order 6, right? So this ordered data is also matching for both the groups. So there is a high chance that they might be isomorphic. So maybe both the examples are uh, same. Now, if they are isomorphic, I will tell you to find an isomorphism. You have the structure of all uh, the el- elements, how they look like. Now, uh, think of the possibility that it is isomorphic to D26.
Sir,
Yes,
so so in general, if we want to compare two groups and see if they're isomorphic, then all these steps that you took first to check if they are both abelian or if they're cyclic, and
cyclic.
then um, then considering the orders. So
Mhm.
if all these steps are taken, then is this sufficient to say that they're isomorphic or that they're um,
Still,
the orders
may
are
not be. In most of the cases, it should be. At present, I don't know the counter example, but in all the like practical purposes, I have found that these actually works out. But
okay?
I don't know if these are sufficient.
Okay,
That's a good question. That if there are same number of elements of the same order, then are the groups isomorphic? So in this case, it's happening, but I don't think in general it will be.
okay, sir.
Okay, so that one has to check. At present, I don't. I neither know the proof or not the counter example, but in most of the cases, we don't really require that. If that is happening, then try to find an isomorphism. Okay. So in this case, check that G1 is isomorphic to G2. But we need one example, so that is there. So now you know uh, uh, the ideal group of order 3 is order 6 is same as S3, and the ideal group of order 12 is same as S3 cross Z2. Although I leave the proof for you, but uh, check it. Or for just a twist, I will write check whether G1 is isomorphic to G2. Still, I'm not confirming that they are isomorphic, but I strongly believe now they should be isomorphic. Okay? Okay. So we slightly go in the other direction. Uh, Now let's come back to the question. Second part says every abelian group of order 12 is cyclic. You agree with that or no?
Mm. Yes, sir.
Why?
So, so again, suppose it's a form Z15, then it's obviously cyclic. So the other form it could take would be 3 cross 5. So in
Huh?
even in that case, any group of order 3 has to be cyclic and any group of order 5 has to be cyclic.
Both are co-prime, so uh, that will be isomorphic to Z m cross n, right?
Yes, sir.
Okay, but what about the second part?
So again, I realized that I just took this for granted. I just thought any group of, if I take any group of order 3 and any group of order 5, since they both
Hmm.
are cyclic, I thought G1 cross G2 would also be cyclic, but now I realize that I need to prove it.
So in case of Z15, you are correct, but in case of Z12, it won't be cyclic. I already told you enough uh, how the abelian groups look like. So from there, can you just tell me whether they will be whether all groups will of order 12, which are abelian, are also cyclic? So what kind of abelian groups can be there?
Groups of form Z5 and even groups of form 3 cross 5. Groups which have order 3 cross groups which have order 5. They both, they also will be abelian.
So you're not audible clearly. Can you just repeat?
So group um, groups which are of form G1 cross G2 where G1 has order 3 and G2 has order 5 or vice
G2
versa.
have order 3 and order 5. How it is possible?
Um, order, oh sorry, you were asking for the order
12.
12, right?
Hmm.
Oh, I thought it was for 15.
Actually, if you take the similar thing here, that
For
Z3 cross Z4, then it will be isomorphic again to Z12.
oh, sorry, sir. I thought you were asking for order 15, the next
Order
question.
15 is
So
clear.
for order 12,
Hmm.
if I take Klein group cross S3, then that's sufficient. That's a counter example.
But that will exceed the order, right? Flying group is of order 4, S3 is of order
Oh,
6,
sorry. Klein group cross Z3.
Z3. Very good. So, take Z to be Z3 cross, I should not write like that, Z2 cross Z2 cross Z3. Then Z is actually isomorphic to Z2 cross Z6, which is, but this is not isomorphic to Z12. Okay. Now, for the third part, I can tell you one thing. In general, groups of order PQ, where P is less than Q and P does not divide Q minus 1, are always cyclic. Okay. So here 15 is just 3 into 5 with 3 does not dividing 5 minus 1, which is 4. Thus, all groups of order 15 are isomorphic. Now it's a task for you to check what if P divides Q minus 1. In that case also, can we say the uh, groups will always be cyclic or no? Okay, for example, groups of order 21. Here also 3 divides 7 minus 1, that is 6. So can we say all groups of order 21 are cyclic? If abelian, then fine. Abelian means we have this decomposition uh, technique. Then in case of abelian, we can write Z21 as at max at Z3 cross Z7, but that is same as Z21. So all abelian groups of order PQ are always cyclic. But can we say all groups of, here I am writing more. I am writing uh, groups of order PQ. So we don't even require uh, abelian thing. Okay. Just check for your fun. Okay. What about the next part? Every group of order 23 is cyclic.
This is true. 23 subtiles.
23 is a prime. Okay. Meanwhile, I also checked what you were asking. So there exist examples where whatever criteria we decided to check, all that holds means the group is satisfying the same property, abelian, non-abelian, and all elements and the order is same, and elements of the same order are have there, and for each order the number of element is also same. Still, the group is not isomorphic. So I think the answer is no. There exist non-isomorphic groups satisfying this property. Okay. Got it. I could have explained you that example, but there is something which is not being taught in the class yet. So you may not understand that example. Okay. This fact also requires something more uh, to be taught, but I'm just throwing the fact here and uh, telling you. It requires the theory of silo groups to come up to this conclusion, and I think silo groups are not being taught in the class. So I will just state it and leave. Okay, so this holds due to since 23 is a uh, any doubt?
No, sir.
Okay, so let me move to the next question then. Today we are going a bit slow because uh, the solutions are not lengthy, but so I can utilize this time to tell you more about uh, some other related topics. I'm just utilizing that time. If you want me to finish this early, then we can also do that.
No, sir. This is fine. This
Okay,
is quite interesting. So this is
okay.
preferred.
I just want to give some additional information that is not there in lecture notes so that you find the topic more and more interesting and connected with some other uh, results that you might see later on. Okay, so let's see this question. Here, Z is the center of a group. We need to choose the correct statements. First one says Z is always a cyclic group. So is it okay to say that the center of the group is always cyclic?
No, sir. So
Example.
if we take G to be the Klein group, it's
Uh,
abelian. So I know that Z is also the Z is G itself, but it's not cyclic.
Not cyclic. So any abelian non-cyclic group. Okay. So is that a normal subgroup always?
Yes, sir.
That I hope you know the proof, right? That is very easy to see.
Yes, sir.
Okay. If the quotient group is cyclic, then G is abelian. I think that is also been done in class, right?
Yes, sir.
Uh, the quotient group is always abelian. What about the last one?
This is not true, but
Then you have to give
I'm
me a
trying to
counterexample.
find the counterexample.
I think the example you already know is just to see that it satisfies this property. The group is something that we have been uh, using in many of the questions. Whenever you think that something is not true, just uh, try to create a counterexample. Creating counterexample is very important in mathematics. So what about S3? What is its center?
The alternating group.
Just identity, right?
Oh, yes.
So two cycles don't commute with each other. You have seen that 1, 2, 2, 3 is not same as uh, 2, 3, 1, 2, right?
Yes.
Here we will get uh, 1 going to 2 and then 2 going to 3. Here you will get 1 going to 3, 3 going to 2. So both are not same. Two cycles are not there. Similarly, you can check three cycles are also not there. Instead of 1, 2, if I just take 1, 2, 3, then what will be the uh, resultant? One is going to 2, 2 is mapping to 3, which is again coming back to 2 is going to 3 and just a minute. So 1 is mapping to 2, 2 is mapping to 3 and 3 is to 1. Here it will be 1, 3, 3 goes to 1, that's it. So both are not same. So three cycles are also not there. What is left? Just identity itself. Then G by Z would be isomorphic to just G itself, which is non-abelian. In most of the uh, exams, uh, if you know enough about groups till order 15 or 20, then you are done. Most of the problems should be solved. The symmetric groups, dihedral groups, and uh, the structure of cyclic groups, abelian groups, if you know these well, then also many questions you can directly handle. Okay, that's why I told you in the very beginning, try to get uh, acquainted with these groups till order at least 10 or 12. Okay, so I hope that is clear. Let me just move to the next question. Now, S5 is a symmetric group in 5 letters. You need to choose the correct statements. Any proper subgroup of S5 is abelian. Do you agree with that?
No, sir. S3 is not abelian.
S3 sits inside uh, S5 and S3 is non-abelian, right? You just take any three symbols and take the permutations containing uh, only these three symbols. For example, if you take 1, 2, 3, then it is the general S3 group, which we know that sits inside S5. So even if you take some other indices, say 2, 3, 4, and then all permutations which have just 2 or 3, they forms a group and that is just isomorphic to S3. For example, what will be there? 2, 3, 2, 4, 3, 4, 2, 3, 4, 2, 4, 3, and identity. There will be 6 elements, and these forms a group, and that is isomorphic to S3 because we're just changing one symbol, replacing 1 by 4. That is precisely the isomorphism. And anything which contains 1 in S3 to the same permutation, but just replace 1 by 4. So symbols don't really matter in permutation groups. So there will not be just one subgroup isomorphic to S3. There will be many. Take any triplet. Responding to any triplet, there will be a subgroup isomorphic to S3 sitting inside S5. Okay. One can ask you how many subgroups uh, in S5 are isomorphic to S3. So the answer is how many triplets you can choose from 5 symbols, and that is just 5C3. 5 choose 3, which is 5 factorial by 3 factorial, 2 factorial. So these many subgroups of S5 are isomorphic to uh, S3. So there is not just one, there are so many. And again, if you take 4 symbols, then that also, so S4 is also sitting inside S5, right? So there will be so many, again, subgroups isomorphic to S4. You can take 5C4 also, 4 factorial, 1 factorial, and that will give you number of subgroups isomorphic to S4. There are so many uh, non-abelian subgroups. And corresponding to each S4, there is also A4. A4 is also non-abelian, right? So again, A4 you know, right? It's a group of all even permutations of order 12. That will be of order uh, 12, and uh, corresponding to each S4, there is also A4, which is also non-abelian. So there, there will be so many subgroups which are non-abelian. Now, this also uh, reminds me of one more example in our previous question. So here we can also take A4. A4 is also of order 12, which is non-abelian. But again, your task will be to check whether A4 is isomorphic to D12. In this case, it's easier to do that because A4 has no element of order 6. In fact, A4 does not contain a subgroup of order 6. That is even uh, much stronger. So A4 is definitely not isomorphic to any of them. You get one more example. A4 also works as counterexample for many things. For example, A4 is the smallest group. It does not satisfy the converse of Lagrange theorem. order is 12, 6 divides 12, but the A4 has no subgroup of order 6. Okay? Okay, then let's get back to the question. S5 has subgroup of order 32. Is it true?
No, 32 does not divide the order of S5.
Very good. So 32 does not divide order of S5. Uh, Therefore, S5 has no subgroup of order 32. Okay. What about the third one? Do S5 has a cyclic subgroup of order 5?
This is true due to Cauchy's theorem.
Can you say a bit louder? Why is it true?
Um, this is true due to Cauchy's theorem.
Okay. Can you give me also an element of order 5?
Yes, so considering one, so if one goes to 2 and 2 goes to 3, 3 goes to 4, so on. If n goes to n plus 1, if I consider that it will have order 5.
Just 5 cycles, right?
Yes, sir.
And you can permute the symbols. Any 5 cycle will have order 4, order 5. This will also have order 5. Okay. Looking at elements is important because next part is also true, but it is not true by Cauchy's theorem. Here also it's asking whether there is a cyclic subgroup of order 6, which is same as asking whether there is an element of order 6. So mm,
Mm. You could take, um, so I could take a 2 cycle and 3 cycle such that they're disjoint. Then they'll always, uh,
very
so
good. So this has order 6 in S5. Now it's your task to check how many elements of order 5 are there in S5 and how many elements of order 6 are there. That will help you to learn how to calculate number of a particular order in Sn. Okay, try to do that.
is
Here
it?
is just cycles, and here is a product of 2 cycles. So just try to see how many elements you can figure out. Although I think there is one exercise, one more problem in which we actually need to do that, but you also try for this. Okay, let me just move to the next part. Which of the following are uh, true statements? First one, I think already done in class, right? First and second one. First one says the order of a K cycle is K. And second one says any permutation can be written as a product of disjoint cycles. So this is already done in lecture notes. So I'm not repeating it. Third one, if sigma has order 2, then sigma is a 2 cycle.
This is not true.
Counter example.
So again, if I take two disjoint two cycles and take their product, that will have order 2, but
They're
it
not
won't be a
cycles.
cycle.
Good. So what about the next one? If sigma is a 4 cycle, then sigma square is also a 4 cycle. I have written counter example, so that's not true. But what is the counter example? If I take sigma to be 1, 2, 3, 4, what will be sigma square? So here 1 is going to 2, 2 is going to 3, 3 is going to 4, and 4 is again coming back to 1. What if I take square of it? Or if you are comfortable with cycle notation, you can also conclude like that. So you will jump one place, right? Instead of going to, so 1 goes to 2 and 2 goes to 3. So you will jump directly to 3. Again, at reaching 3, you need to jump with one symbol. So 3 goes to 4, 4 goes to 1. So if you jump again, you will reach 1. So one cycle is closed. So this will be 1, 3. Same happens for 2 and 4. So you will be just getting 1, 3, 2, 4. Now, if uh, you can observe uh, that if sigma is a, again there is a check for you. If sigma is a L cycle and GCD of M and L is 1, then sigma M is also an L cycle. That is first point. Is an L cycle. Also an L cycle. I should write L here. But second thing is, if sigma is an L cycle and M divides L, then sigma is a product of M many uh, L by M cycles. For example, instead of 4, if I would have had 6, then what would have changed? I would have sent 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and then 6 would have come to 1 again, right? 1 would have, so taking square, oh, then sigma raised to m I should write here, no? If sigma is an L cycle and m divides L, then sigma raised to m is a product of m many L by m cycles. So 1 would have gone to 3, 3 would have gone to 5, and then 5 would have come back to 1. So this would be 1, 3, 5, and 2, 4, 6. So there are 2, then m is 2. This is sigma square. Too many 3 cycles. Okay. Now that is good enough. Both these facts are good enough to calculate any power. Can you tell me why? At least the length of length you can conclude. So if its GCD is 1, then it's an L cycle dull. If its GCD is not 1, then there is something in the common factor, right? So for example, if there are two numbers m and l with GCD not equal to 1, then what you can write? You can write m as d times r, where d is the GCD of m and l, and r and l are co-prime, right? If two what is GCD? GCD is just the highest common divisor, right? So whatever is left after dividing with GCD has to be co-prime with the other number, right? You got it?
Yes, sir.
Or there is a doubt?
So far, I got it, sir.
Okay. So now if you want to see what is sigma times m, you can write sigma m as sigma times dr or sigma times rd, which is same as sigma r raised to d, right? This thing has co-prime, uh, uh, this is co-prime with L. So this will again remain as not the entire thing. This part will again be a L cycle, sigma dash raised to d, which is an L cycle. And d divides L. So now once d divides L, you can use the second part and then see that this will be a product of d many L by d cycles. So you know the cycle decomposition for any power. Okay. For example, if you have 4 and 6, sigma is a cycle of length 6, then what will be sigma 4? You can write it as sigma 2, sorry, sigma uh, here, right, GCD is 2 only. So sigma 2 raised to 2. So sigma 2 is dividing 6. So this will be product of too many 3 cycles. Again, you have square and still they are disjoint. You can take 1 3 cycle raised to 2 and other 3 cycle raised to 2. But now this is of length 3. If you take square, the length will be same. Again, here also the length will be same. So sigma 4 will have the cycle decomposition like this. It will be product of 2 3 cycles. Okay. So what you got? Finally, you will have d many cycles So here the GCD is 2, so you have 2 cycles. And length is captured using this thing, this kind of process. You take the either the co-prime part first, and if the co-prime part is 1, then you take first power, and then in the second you take the d many powers, and after that step you will get the co-prime thing, and then it won't change the length. So is it fine?
Yes, sir.
So this is again something extra I told you. So maybe I can just erase it. Not part of problem. But you need to check these 2 facts to make sense of whatever I said. And this is easy. Just basic routine calculation. If you do, you will realize that both these facts are true. Okay. Okay. So we are also done with this question. Now let's move to the last problem. The symmetric groups are extremely important. If you want to continue in mathematics and you want to read group theory further, have a good hold of symmetric groups. Okay, that's the final question of this assignment. Let S4 be the symmetric group on 4 letters. Let A denote the number of elements in S4 of order 2. B denote the number of elements in S4 of order 4. We need to choose all the correct statements. So, uh, can you tell me how many elements of order 4, order 2 are there in S4?
There are 9 elements of order 2 and 6 elements of order 4.
How you calculated it? I couldn't hear. Hit and trial or
Um, so if I take any 2 cycle, then I know that the order is 2. Also,
okay. Hmm.
um, if I take two disjoint cycles, 2 disjoint 2 cycles, even then the order will be 2. So I need
Order will
to
be there.
consider uh, n- both both of these numbers. So for the just 2 cycles, there are um,
Hmm. Okay. Just for 2 cycles, how many elements are there?
there are 6 elements.
Hmm. Why?
So
So you have sigma to be of the form A times B. There are 4 possibilities to choose the symbol A. Choose the symbol A, right? Once A is chosen, there are 3 possibilities to choose B, right? So we are having 12 possibilities. Is it correct?
um, but There will be repetitions, right?
What kind of repetitions will be there?
So first, if I choose some A,
Hmm.
then I know that there are three possibilities.
Hmm.
So if I take the next element,
Hmm.
so suppose I have A, B as one
Hmm.
of the possibilities here,
Hmm. Hmm.
then I would for the then if I for the so that I would have AB, AC, and AD. Then I would consider the two cycles with B in the first place.
Hmm.
But then BA would be same as AB. So
Very
all
good.
those need to be removed.
Removed. So also the element also the elements AB and BA are same in S4. This implies there are 4 into 3 divided by 2 many 2 cycles in S4, right? Now, what about this?
There are three possibilities.
How
So,
many possibilities?
um, three possibilities.
3 possibilities. Why?
So suppose I fix A and B,
Mhm.
then there's only one option left for the second cycle. So I
Right.
just need to see how many ways I need to have for the first cycle. So again here for just one cycle, previously it was seen that there are six possible ways. But then
Mhm.
here, since there are we need to consider the second cycle itself, there will again be repetitions.
Very good.
So we only have 6 by 2, which is 3.
Very good. So, another way to see this, which is very general, if and will work if you have cycles of different length. So, 4 possibilities for this, right? We will take care of repetitions later. 4 for this, there is 3, there is 2, and that is 1, right? And now there will be 2 repetitions because AB is same as BA. There will be 2 more repetitions due to the fact that CD is same as DC, and there will be 2 more repetitions because ABCD can also change place, right? Now, if you look at the number, it will again come out to be 3. Okay. Now, why I am telling this method? Because suppose if you want to see how many of in S7 you want to see how many uh, permutations are with cycle decomposition 3 comma 4 are there, then the same thing will work, right? You need 7 6 5 for this 3 cycle, and then for 4 uh, you need uh, 4 3 2 1 because this is already fixed. So that means A B C D E F G. But if you come to the repetitions, there will be 3 repetitions for this, or not just 3 repetitions. This will be 3 factorial in how. Oh, I'm missing something. Yes, there will be just three because ABC is same as BCA is same as CAP. So just in same cycle type, you need to write the same order. So three is for this and four for this. So these many elements will have this decomposition in S7. So this kind of thing works in any case. You just first choose the symbols and then divide by the possible repetitions. Okay. But whatever you said is also very nice. So there will be 6 plus 3, 9 elements of order 2 in S4. What was the second uh, problem? It asked number of elements of order 4. Similarly, can you tell me
Mm. Here the six number of them.
6? Why?
So again, for if I take any four cycle, I
Hmm.
get the order to be four. So again, if I consider the possibility, all the possibilities, I have 4 factorial. But then I know that ABCD is same as D, ABC, and so on. So there are 4
Hmm.
repetitions. So that would
Okay.
be 4 factorial by 4, which
4
is
factorial, which is 3 factorial, and that is 6. Okay. So in general, number of n cycles in Sn is n minus 1 factorial by the same. But is it also the number of, is it also the number of elements of order n in Sn?
yes, sir.
You got the question?
Yes, sir. So there are no other uh, cycles which give other than 4 cycle which give the order 4.
Now, here it is fine. I am saying in general, is it true?
Um,
Here it is fine. Since uh, elements of order 4 in S4 are 4 cycles only. Therefore, what was the notation? B. B is equal to 4, only 6. Now, my question was, in general, we can also say that the number of n cycles in Sn is n minus 1 factorial through the same idea. But is it also equal to the number of elements of order n? So what you need to check, you need to check that if you have n symbols, then are there permutations which are not uh, n cycles, but their order is n. Can you find such an example in S6? Till S5 it will be okay, but in S6, 6 cycles gives you order 6, right? But are there elements other than this which are also gives you order 6?
Oh, if I take the 2 cycle 1, 2 and 3 cycle 2, 3, 4, 5. Oh,
Right.
mm,
So in general, that is not true that uh, number of elements of order n is same as number of n cycles, right? Till S5 that is true, but not true in for S6. Okay, so that completes the uh, assignment 5. We still have some time. We also started a bit late, so we should go till 8:15, I guess. And um maybe we can start the next assignment if you're okay.
yes, sir. So for these, I haven't uh, written the proofs, but still, I think I can uh,
So assignment 6 you are
try.
telling?
Yes, sir. But still, I have gone through the lecture notes, so
Okay.
I can try. So it's
I
fine.
hope the deadline is already over.
The deadlines over. Uh, so, sir, sometimes, uh, so in every question, I know that there are exactly two correct questions, and so some sort of guesswork is involved. But usually, before the live session, I write the proofs completely, which I haven't done for assignment 6.
Okay, but one more issue is already uh, okay. So is it the case that exactly two are true
Yes, sir. So far, that has been the case.
for all options and for all problems?
Yes, sir.
I never realized that. But in final exam, you may not get that.
Yes, sir. But I
So
do them, but right now I haven't done them. But I usually
so
write the proofs. I haven't done
be
that for
aware of this
assignment
that
6.
this might be some coincidence in final exam. There won't be these cases. Okay.
Okay, sir.
Anyway, I'm not going to prepare the paper solution, so you don't think that you have caught the trick and it will change.
No, sir. No, sir. I won't use it.
So, uh, so as I was, but there is one problem if we start discussing assignment 6 for Tuesday class, we need to do something else because assignment 7 deadline is after Tuesday. So what we can do, maybe we can discuss some practice problems from assignment 5. They are different from the original problems, or they look similar. There is at least one or two problems I can see which are of different nature. I think we can discuss that. Assignment 6, let's keep it for the next class, right? On Tuesday also we have one class.
Um, Okay, sir.
Otherwise, uh, for the entire class, we need to discuss some other stuffs. we will have plenty of time, so we can do that. Yeah, so this is from the uh, practice assignment. So let Sn denote the symmetric group on L letters. If sigma is in Sn, then the order of sigma is at most n factorial. Is it true?
Sir, can you show the question?
Oh, sorry, I haven't shared the screen. Is it visible?
Yes, sir.
Okay. First problem, is it true?
Yes, sir.
Why?
Mm. So for Sn, the order is n factorial. So
Good. So for any group G and small g belongs to G, order of G divides order of G, which implies order of G is has to be less than order of G, and thus here, since order of Sn is n factorial, therefore order of any element in Sn is at most n factorial. Okay. Sn always contains an element of order strictly greater than n. Is it true?
no, sir. I could take S3 for example. It doesn't have any element of order greater than 6, greater than
Even
3.
S, in this case, S2 will also work because it's saying n greater than equal to 1. Till S4, this should be okay. Any example till S4, it's fine. But in S5, there is an element of order 6. Okay, you got my point?
Yes, sir.
For counter example, you can take even S1, S2, S3, and S4. Anything will work. Not in S5. What about S6? Is there an element of order greater than 6 in S6? See, 7 cannot be because 7 is a prime, so you need a prime, you need a cycle of length 7. That's the only option. For 8 also, it is a p raised to n type. So you need at least an part of length 8. Same for 9. 9 is also some prime power. Now for 10, you can reduce the symbol till 7. You can take one 2 cycle and one 5 cycle. So in S6 also, this will hold, right? S6 cannot have an element of order greater than 6. What about S7? In S7 also, no. We just saw na one 2 cycle and one 5 cycle will have order 10. Similarly for S8, one 3 cycle, one 5 cycle. For S9, one 4 cycle, one 5 cycle. Order is 20. In S10, one 3 cycle and one 7 cycle. Now check if this continues further. I will expect yes. For S11, you can take uh, 1 7, 1 4 cycle, but I don't know whether the proof is there. But I think after some n, this should be the case that uh, it should hold that Sn always contains an element of order strictly greater than n. But one need to check whether it's been proved or it's an open problem. That's also I don't know. But the pattern says that for larger n, it should be the case. Okay. Now, if sigma 1 and sigma 2 are elements of order 2, then sigma 1, sigma 2 has order 1 or 2. Is it true? Hello?
If there
Am I
is,
audible?
yes,
Huh?
sir, I was thinking. If
This
they're
we have already
disjoint, I know that they're true, but trying, I'm not sure if it's true when they're not disjoint. I'm
just
trying to find an example.
yeah. So you have seen that example many times. What it is saying, if there are elements of order 2, will the product will also have an element of order 2 or 1? When can it have 1? It can have 1 only when one is an inverse of other, right? But if that means if there are 2 cycles, what is the inverse of it? It's the same cycle. So if you take two distinct 2 cycles, will the element, will the product of it uh, have order 2? So many times we have seen that counter example. Sigma 1 just take 1, 2, sigma 2 to be just uh, 2, 3. What will be sigma 1, sigma 2, right? And greater than equal to 3, of course, you need. It has order 3, right? Not 1 or 2, correct?
Yes, sir.
Now tell me what about the next one?
Now I take 1, 2, 3 and 1, 3, 2. And
1, 2, 3 and 1, 3, 2 will be inverse
oh,
of each
it will
other.
have order 1.
If you take any cycles of any length L or length M, if they have just one symbol in common, the resultant will have length L plus 1 M. That's a bonus fact. The criteria is they should have exactly one symbol common. Okay, cycle of length M having just a unique symbol common will give you a cycle of length L plus M. For example, if you take, first of all, I will need to take n greater than equal to 5, sigma 1 to be 1, 2, 3, sigma 2 to be 3, 4, 5. They will join at uh, 3. 1 going to 2, 2 going to 3, 3 goes to 4, 4 goes to 5. That will be the resultant. It has order 5. Okay, clear?
Yes, sir.
Okay. What about the next problem? Sigma is in Sn, it has order 3. That sigma square also has order 3. If you want, you can go with the solution of this by just multiplying it again with the same element, or you can use the trick. You can use the fact that I stated earlier. Here, M is co-prime with L, so sigma M will have length L only. Sigma square will also have length 3. But here the good thing is we are looking at uh, what to say. We are looking at prime numbers, right? So uh, for prime, the good thing is after taking its power, the order will not change. Can you tell me why? Let me just solve it in detail. In general, this holds for any group, not just Sn. So let G belongs to G. Let G be a group, and G belongs to G be such that order of G is equal to 3. Now, case 1, order of G, order of G square. This definitely mean uh, uh, Okay, let me just write it like that. Since order of G is 1, order of G square, sorry, order of G is 3, G square cannot be identity, right? G square cannot be identity. Why? Because if that is the case, then order will become 2. So order of G square cannot be 1. Now what if order of G square is 2? If order of G square is 2, then G square raised to whole square is 1, which implies Z4 is equal to 1. And that will implies G cube dot G is 1. But this is already identity. This will implies G is 1, which is a contradiction, right? So that cannot be the case. Now G square cube is G cube square, which is just identity square. So identity. So 3 is the least number such that G square vanishes at 3. So order of G square is 1. Sorry, 3. Okay. Just a second. No, something like that. Take on. So you got it? Same thing try to do with any power. What happened if uh, you are giving the order of some G and you are asked to calculate the order of some Gm? Again, the same pattern you will see that co-prime and prime thing and what is the GCD. These two things will play a good role. What I'm saying, if order an element G is n, what will be the order of an element G raised to m in terms of the order of G? Here, the co-prime thing is there, so the order remains the same. And in general, if the order of G is something n, and then the order of G raised to m, where m is co-prime with n, will also be n. Okay, but you need to check this. And what happens if it's not co-prime? Then your GCD will come into picture. Okay. Clear?
Yes, sir.
So this has nothing to do with Sn. This question can be asked for any n, okay, for any group. Okay. Okay, then maybe one more question we can discuss and then we will stop. Just taking the fourth problem from okay, to keep it here. You're also solving practice assignments or no?
Mm, yes, sir. I'm solving them.
Good. This is also an extra question. Again for Sn, the number of odd permutations is asking. So First and second part are actually one part. Do you know the number of even permutations?
Yes, sir.
How many are there?
N factorial by 2.
Okay. So since number of even permutations is n factorial by 2, how many of them, how many will be odd?
Again, N factorial by 2.
Because the permutation is either even or odd. Even n factorial minus n factorial by 2, that is n factorial by 2. So this is not correct, but this is correct. What about the third one? Number of elements of order n in Sn is n minus 1 factorial.
Oh, this was seen just in the previous
Huh?
question. So,
So this we have checked. So that by chance came here in practice assignment. So this is already done, right? In uh, previous problems. And for third, the counter example is S6. In S6, all 6 cycles are of order 6, and number of 6 cycles in S6 is 5 factorial. Also, permutations of the type A, B, C, D, E also have order 6. There are many more. Okay. So this is not correct, but this is correct. What about number of elements of order 5 in S5? This is correct. Only in S5, uh, the number of n cycles is equal to number of elements of order 5, and which is 4 factorial, that is 24, right? So here your that prediction failed. Here we have more than 2 options correct, right?
yes, sir.
So that was also happening in practice assignments.
Oh, in the practice assignments, it's not the case that only 2 of them are correct.
Okay.
But in the actual assignments,
Then,
it's always the case that only 2 are correct.
then that may be some coincidence. Even I never realized it. But it's happening. That doesn't mean it will always happen. But okay.
Yes.
What about number of six cycles in S6?
Mm.
That is also 240. That because that is just 5 factorial, right?
Sir, 5, 5 factorial is 120, right?
Right. Thank you. So I just need to cross this. That's it. Okay. So this, thank you. This is not correct. Okay. I think uh, we can stop here. If you have
Sir, you are not audible.